So welcome back. So now I will be talking about patterning, and I will talk about what we have been developing in our lab together in collaboration with Professor Owen Banerjee's lab, the microbubble lithography. So, and we will show that what are the applications of this microbubble lithography in catalysis. And as the name suggests, so you have seen it in the last class where we have shown that how you create the bubble, you translate the bubble, and then you make patterns, right? So when you have systems in place, it's also important that your systems get smart. They can write things, and writing is nothing but coding. So you put some information and then you transfer this information, and then that information will have some meaning, and when you are looking at it, the information gets across and you are able to decipher the information. So it will be nice if chemical systems can have this capacity so as to be able to code and decode, right? So, and we are able to write these type of materials on simple surfaces like glass surface, ITO electrode surface, and so on and so forth. And we are able to do catalysis with this. And what is the meaning of this microbubble lithography? So we create bubbles which are microscopic. So we create microbubbles. And then with these microbubbles, we are able to create patterns because there is this condensation, what I talked about in the last class, right? So you have a laser, I just repeat it again. So you have a laser trap or an optical tweezer trap, then you have convergent lasers, right? And then they heat up the local reaction environment in the sample chamber of this optical tweezer, and they create bubbles. And these bubbles, these microbubbles, have a Gibbs-Marangoni type convection current around them, right? And these convection currents would be created because there is a surface tension gradient, because on one surface is more heated than the other surface in the sample chamber, and this will give rise to this convection current. And when you have this convection current, then when you move the laser bubble away, then they cannot get the time to move. They indeed then condense with each other and they crystallize and form patterns. And that's how we are able to write patterns, for example, like this, which looks quite neat and clean, right? So you can just write these patterns on surfaces as you want. And what we have seen, that people from schools, even younger ones than you, they have come and they have played with the joystick and they were able to make houses, gardens, whatever drawings they wanted to do with these joysticks. So it's that much of a control that you can exert with these type of systems. Now, what we want with this type of writing is, our future question which we would like to ask is, can we enable catalyst systems to write their own catalytic codes? That's an ambitious challenge, but that's what we would like to do maybe someday. So that's the overarching view of this. So now here writing is coding, and we would like to partition or to create the codes by means of creating partitions in there. And we would like the catalyst systems to be able to write their own partition, their own codes in there. So this is how it looks like. So for example, you have this type of microbubble. Now around this microbubble, you have the convective flow, right? So you have just the convective flow moving around the microbubble, and you have here at one point you have the heated area, and here you have the cold or cooler area. And because of this difference in this hot and cold region, you have the convective flow. And I want to remind you that these are all experimental results. So these are not theoretical results or whatever. These are all hard experiments, and these are all experimental results which I am showing you. Now you are able to have this convection current, and then you are able to form this type of conducting pattern. And if you are interested, I would invite you to read this review with Owen Banerjee and myself in Nanoletters, which is published a couple of years before, where we archive this whole study which we are going to present, or which I'm going to present. So what happens here is the following. So you have a system where you have the light source and you have the sample chamber. In this sample chamber, you have the SOM dispersion, and this is very, very general. Now we have shown that it not only works with SOMs, it works with any kind of materials. But of course, with SOMs, it's a little bit easier because they are more tunable and they have a diverse range of properties. That's where it's a unique system which is applicable in these cases. Now, this work first was discovered by this guy, Vasudev Roy, who is now a professor or an assistant professor at IIT Madras. So what Vasudev found when we were doing these type of works is that we were trying to trap SOMs. That's all we were trying. We're not trying anything else. So in optical tweezer, we have these two Gaussian beams, and within which we wanted to have the SOMs trapped. Just tweezer is like this, right? So you hold it. So we wanted to hold the SOM in there. And what we found, what Vasudev found, is that whenever he's trying to do a pattern of, whenever he's trying to trap the SOMs with these optical tweezers, there was a jet of an ink-like thing that was coming off in course of this patterning. So this was an optical kind of a thing, and he was really persistent, and he then did a lot of control experiments. We did a lot of control experiments to understand what is happening, and then we were able to see that what is happening is the following. So I will show you again. So you have here the sample chamber and the cover slip. So in between the sample chamber and in between the slide and the cover slip, you have the sample chamber, and here you have the bubble. Now this is the microbubble. When you are shining laser, we see the bubble, this tiny bubble grows. It grows in size, right? Because it gets heated up. Now when it gets heated up, it's not isolated. It has all the SOMs around it, right? So because it has all the SOMs around it, so then what happens is that when you have this heated bubble, you see a current of SOMs around the bubble. This is because of this, as I mentioned earlier, the surface tension gradient. Now when you have this surface tension gradient, the SOM bubbles, the SOM units, they come from the heated part to the cooler part, right? And then if you move the trap, the laser trap, if you move the laser away, then there are two possibilities for these SOMs, right? One is to move with the bubble, just to move with it, or the second possibility is not to move with the bubble, which is less likely. At least that's what we thought intuitively. They will perhaps stay back. And that's why in science, as Professor Kari Risanen already mentioned in the first class, that you should believe, or you should go by the data and with your brain, not by the tendency which you are going to have when you think a little bit, because you have to be careful with your thoughts, and you always have to base your thoughts on data, hard data. So what we saw is that this type of phenomena, this type of transition or phase transition is happening, and that is why Vasudev was seeing this jet black ink-like thing that was forming as he was translating the bubble, right, which was not expected. So if you don't translate, if the bubble was moving, then there should not have been any translation, right? So there should have been no translation, nothing, but you will have the particle moving with the optical trap. That is what was the original idea. But then this was what we saw, and then with this transition we were able to write, or Vasudev was able to write patterns, and with this we wrote patterns like IISER. You can read it. So that is what we wrote, the name of our institution. And now, as I said, we can write any kind of pattern, whatever we want to write. Now, and we were also able to put some other units like fluorescent molecules in there. We put carbon nanotubes in there. We were able to pattern all these together with the SOMs. And then we thought that can we use them for some concrete application, because that will be quite interesting, because then you can miniaturize catalysis, right? Because it's always, there is a demand that if you can do miniaturization and if you can do reactions on confined surfaces or on small length scales, because that gives you an advantage or a new opportunity to do multiple turnovers, right? So that means you can reduce the size, and that's essentially one of the guiding principles of nanocatalysis, which you are familiar. So this is of course not nano, because with light, again, Kari showed in the morning the electromagnetic spectrum, entire electromagnetic spectrum, and you know that with light here we cannot go to nano. We can stay up to a few hundred nanometers. Why? Because visible light has that limit. So you go to the limit of visible light with which you can do these type of patterns. So you can have patterns with width of few hundred nanometers. And not only that, what Vasudev also showed, you can see different widths of these type of patterns, right? So this is more thin, this is thicker, this is even thicker. That happens with the speed of translation of your laser tweezer. So if you translate them very fast, then the bubbles do not have time to grow that much in size. You pull them very fast, you get thin patterns like this one. But if the residence time of the bubble with the laser, the contact time or the residence time, whatever you call it, if it is higher, then they have more time for residence. Then you get thicker lines or thicker trails. And if you reduce the time even more, you have really big, dark trails, which you can even see with naked eyes. So that's kind of the power of this. So you can control the thickness or the width of these type of bubbles. And this I have shown you. So then what, with Vasudev, we also joined hands with Benthang and Professor Cho Shilan from Jilin University. So they made this type of porous organic frameworks for us. And then we were able to put these MO7 type units. This is positively charged, this is negatively charged. This is a very simple unit. You have seen this unit again earlier, right? So we try to work with MO7 type units because this is the most simple polyoxymetallate for us. We don't want complex polyoxymetallates because then the interactions become difficult to understand and it becomes difficult to go over there. So then we were able to see that when we are loading these SOMs on the POFs or porous organic frameworks, there is a domain where you have unstable dispersions, right? Unstable dispersions are like this. So I'll tell you a little bit about the dispersion so that you know it. So for example, if you take stones, right, and if you put them in water, if you take sand gravels, you put them in water, they immediately settle in the water, right? But if you take, for example, sand grains of sand, you put them in water, they will not sink that easily, right? If you shake them, it becomes a little bit turbid kind of a thing. But if you take silica nanoparticles, SiO2 nanoparticles, and this is a famous method which is known as Stoiber's method of synthesis, which is with silica, so which is with TEOS, tetraethyl siloxane, and then you get a clear turbid solution. You get a turbid solution. There is no question of settling down whatsoever, right? That's because you have then charges on these particles which repel each other. And this repulsion is stronger than the gravitational field that is acting on them, on the stone, for example, which would lead to its settling. You understand, right? So this repulsion would give them the stabilization. So essentially you have charge stabilization in these systems. But when you do not have charge stabilization, when you do not have this type of repulsion, then you have unstable dispersion. That's what it is called. So that means it will settle down. So if you do the experiment, and you will see when you have this SOM and POF, they will settle down, and but after a certain loading, you see that they form stable dispersion. So you see when the ratio is 20-fold, 30-fold, and so on and so forth, they're stable. But with less, around 10-fold, they are not stable. So that means they are just forming unstable dispersions, right? And then we looked at the IR spectroscopy, and here is another important point. We could not get the crystal structures here. Why? Because we are in dispersion. So we are totally working in dispersion. There is no translational periodicity, so we cannot have crystals. So we are having liquids, and for liquids, of course, you can get structure, but that is by static light scattering. In this case, we didn't do static light scattering, which is exactly same principle as the one Curry will show you. It has the structure factor, it has the form factor, is exactly the same. Only difference is that you have to assume in static light scattering the form factor to be that of a sphere and then solve it. When you do dynamic light scattering, you also again do the same thing, but in that case you have to find the diffusion coefficient, and this diffusion coefficient finding also has to have an approximation about the shape of the particle. So now, having said that, then that's why we looked at the IR spectroscopy, and we were able to convince others and of course ourselves too that you have a combination of this SOM and POF. And then we used this lithography, and we were able to write patterns like this. Now, and you can see these patterns. So these are really high on the surface, and then as you translate the laser, like the way I am doing, literally you do it on the microscope stage and you get this type of patterns. Literally you do this and then you will get it. And then when we do a line scan of on these particles, what we observe are these elemental compositions. So you know that on these particles you exactly have these units together, right? So that's what the power of this technique is. And when we do this, we also see that when you do a cross-sectional line scan, I have not shown it, but it's like this, then you see at one point there is nothing, then suddenly it goes up and then it comes down. This is the molybdenum, the yellow one is the molybdenum, the green one is the oxygen, and the red one is the carbon, and the violet one, you cannot see it here, but I can see it, but you cannot see it from there. That's the phosphorus. So you have all the material, all the elements that are present elementally, right? And we also did select area electron diffraction, which you have heard also in the second class from Curry, that you can do electron diffraction. So select area electron diffraction, and we were able to see that they were like liquids. So we do not have a crystalline lattice or something, we just have liquid-like structure. So now what we were able to do is that this MO7 based SOMs were likely to get into the crystalline domain, but only in a macroscopic scale. Now what we did then, we looked at the Raman modes, and this is what we found, that there was a difference in the Raman stretches, and that's because you have weakening of the bonds. And we also did porosity measurement, and what we found interestingly is that the pores sizes were changing. These were the pores which were in the pristine compound, after doping with the MO7, these pores totally disappeared. So that means they are going and sitting on the pore and creating a surface area which is accessible for your reactants. And the stability, we also checked it with the TGA. And then what we found is when we do the reaction, we did the reaction, and this is a work, as I mentioned you, this was done by Preeti Thomas. So when she did this reaction, she was able to show that with an external standard, there was a possibility that external standard was DMSO. So we added DMSO as an external standard, and using benzoic acid. So because we were studying benzaldehyde oxidation to benzoic acid, she was able to show that this peak, which was signature for the benzoic acid, it slowly increases, and it only increases on the trail. And if you go out of the trail, there is no reaction whatsoever. So that's why we called it site-specific reactivity. And not only that, we were also able to see that this type of sigmoidal kind of behavior, which indicates that there is a heterogeneity in the system, and this is very typical for heterogeneous catalysis, because you have a cooperative phenomena that happens during the catalysis, and that's why you have this type of system. So this is a signature for any kind of heterogeneous catalysis. And we found that that's what I was saying. So we did reaction, for example, over here, right? So when we did reaction over here, we were able to get this type of conversion with respect to benzoic acid and DMSO. But when we move away from this, so when we do reactions over here or over here, we got a flat line. So that means there is no conversion going on. So it's very site specific, and you really have to see that you are putting your product, your reactant, just on the trail or just on the surface of these materials. Then we thought, okay, it's fine. Can we take up some more challenging reactions? Can we do some little bit more challenging reactions? Now, what is a little bit more challenging reaction? We thought, can we do polymerization with these type of systems? Earlier, this was a work that was done by one of my earlier undergraduate student, Atharva Sahasrabuddhe, so who is now in MIT. So he did this reaction, and you took the polyoxymetallate, he shined light onto this. So when you shine light onto this, then it goes to the charged state, excited state. Now when you have in this excited state, you have butyl methyl imidazolium. Now butyl methyl imidazolium has these hydrogen atoms over there, so that can be transferred. So it's like a hydrogen atom transfer. So when you have this transfer, then you create an imidazolium cation radical. So now once you have this imidazolium cation radical, you have this oxometallate is being reduced. Now if you take this oxometallate, put it in open air, then this oxygen would get reduced into water, and your oxometallate or polyoxometallate is regenerated. So that's how you create this closure loop. And here this butyl methyl imidazolium radical would then polymerize any kind of monomer, whether it's a vinylic bond or an allylic bond, it can polymerize these units, right? So this was done in conventional condition. And what we also found in this type of reactions is that you have these closed pockets, elliptical pockets of butyl methyl imidazolium, which has a diameter almost of around 1 nanometer and width of around 0.46 nanometer. Now, by the way, this is crystal structure, yeah. So this is exactly from the crystals, and this is from the diffractometer. So we get the crystal structure, and then we were able to see these type of pockets. So these type of hydrophobic pockets were responsible for holding the nascent oligomers which were being created. right? And it was then what we observed is that we changed the loading. So once we change the loading, what we find that the molecular weight increases. And this is very, very simple, because when you have a radical polymerization, you know that if you have lesser and lesser radical, because you are loading initiator, right? So you can change the initiator, right? So if your initiator loading is higher, so if you put more initiator, then this ratio is small, so this is over here. So you see the molecular weight is less if you add more initiator. And this is from your basic knowledge of polymer science, that if you add more initiator, then you have much more radicals. Now those radicals, because they are much more, the chain length that you can create with these type of radicals is much shorter, as compared to if you put less radical, and then you get much higher polymeric weight, molecular weight. And this is what we had observed earlier. So we thought, okay, now, yeah, so this shows that it's a free radical pathway, where, as I said, you decreasing the initiator increases the molecular weight. So this is one of the acid tests for free radical pathway. So we thought, okay, can we do these type of reactions with different monomers? And we were able to do it with different monomers, and we put some radical quenching agents, and then we were able to see the same kind of effect. But as you can see, the scope is not bad. We have styrene, butyl methyl methacrylate, vinyl acetate, methyl methacrylate, and so on. So what we were able to see, for example, is that this reaction goes perfectly fine, and you have a very nice recovery. And this is almost 100% conversion, and you have a very nice recovery that goes on. And you see in the reaction in the lab how it looks like. So after the reaction, this looks a little bit dark. You now put it in open air, right? And then you reoxidize this oxometallate, and then it comes back into its colorless native state. So that's how it's a totally recoverable reagent, recoverable catalyst. And then the question that we asked is, can we do catalysis, this type of catalysis, under optical tweezers? That was the question, because we have done it under normal light, right? So this type of light, can we do this catalysis under optical tweezers? So then again, Shontu came up with this nice idea that yes, we can try. And so what we did is then combined MO7 with pyrrole. And then what happened was very, very complicated. We didn't expect it to be that complicated, but it was really quite a complex thing. So what we saw is that there is a creation of a pyrrole radical, which would then combine with another pyrrole unit, with the conversion of this reduced MO5 into further MO4, and then that would lead to a kind of a clicking, and then you have a full polymerization. And not only that, you have these MO4 units which are forming MO2 type units, and they are acting as a dopant, because this is electron rich, and they are acting as a dopant, and they are doping this and forming this very interesting polymer SOM composite. We didn't expect it when we started doing this reaction, that it will be so complicated. And this work again was done with Owen Banerjee, because we do works jointly on this type of themes, and it really took us very long to understand what's going on, because it was very, very complicated. And then what we found was following. So Shontu was able to form these patterns, and then you have this kind of topologies where you see sharp valleys on the pattern. So these are pattern pictures. On the pattern you see sharp valleys, and you can form a little bit more rounded structures. Now this gave us the first time hint that there might be some soft polymeric materials which is enabling us to form more rounded structures. because crystalline patterns would be sharp and straight. So this was a very important observation from Shontu, and then we deciphered this entire pathway with XPS and so on and so forth, the full story. And not only that, then what we found is when we change the SOM concentration, then we saw that there is a certain concentration of SOM at which there is a maximum conductivity. So we then measured conductivity, and by measuring conductivity, we were able to see that we have in fact made plastic conductors. So plastic conductors, you know that polymeric things which are conducting, so those are the plastic conductors. So we have come across plastic conductors, and the conductance is also not that bad. It's around 600 Siemens per centimeter. Not only that, when we used it with pyrrole, we also got these type of conductivities, and we saw that beyond a certain concentration, the conductivity goes down. So that means you have a certain available area on the plastic polymers, which are the pristine polymers, where the SOMs can be accommodated. But beyond that, you cannot do that, because you are then disturbing the intrinsic conductivity of these type of polymeric units. So we were quite happy to see that what started out as a simple trial experiment for forming polymerization reaction, or for doing polymerization reactions with oxometallites under optical tweezer, resulted in 3 distinct phenomena. What are those 3 phenomena? Number 1, you have the pattern formed, right? That's the simple phenomena. Number 2, you have the reaction going on. So you have this reaction where you are creating MOO2 type systems. And number 3, these MOO2 type systems are acting as a dopant, and then they are combining with the polypyrrole and thereby forming the plastic conductors. And we were able to show it with other monomers like aniline and so on and so forth. So this shows the possibility of sometimes emergence of synergy which are not that planned, because we didn't really plan that it will be a conducting polymer. We just wanted to do a polymerization reaction, and we ended up with a conducting polymer altogether. Next, okay, this is already published now. So next is nice work by Rakesh and Khokon, who is in the audience. So what Rakesh did with Khokon together, they wanted to do a pattern, but this again was a complicated molecule. It was tetrabutyl ammonium together with phosphovanadate and tungstate type unit. So where you see this tungsten 9 is substituted with PV3. Now these formulas seem very intimidating or complicated, but they are not. You can close your eyes and deduce these formulas. How? For instance, initially you have a PO4, that is phosphate, right? PO4. Now a PO4 is a tetrahedron, right? So now a tetrahedron has how many vertices? 4 vertices, right? So now each vertex, if they have a tungsten 3 cap, then this tungsten 3 cap means you will have how many caps? 4 caps at most, right? That means that will make it PO4 W12, right? Because each one is a W3 cap, so 4 caps will make it W12. And then oxygen will be how many? Because these are tungsten oxide is WO3, so then it is oxygen 36, right? So then PO4, 4 oxygen, 36 oxygen makes it 40 oxygen. So that's your 40 oxygen, right? And you not only have here tungsten, but also you have a vanadium cap. So instead of 3 tungsten, if you put 3 vanadium, then you have PV3W9O40. Okay, so that's a polyoxymetallate, right? So we took this polyoxymetallate, and these are the molecules whose crystal structures can be determined from X-ray crystallography, and as you will learn from Kari. And also there is a lecture by Professor Shamor Dash who will talk on the polyoxymetallates in application of crystallography in polyoxymetallates. So now anyway, so what then they said that they took this, and then what was observed, when they have this pattern, they did everything like regular, right? So like the way they were doing this full patterning and so on. And then when they did the pattern, then they did aniline, and they were able to oxidize aniline into nitrobenzene, which is not trivial because this is a tough oxidation reaction, and they were able to do it under ambient condition. So I was very confused. I insisted that they repeat it. We did several control experiments, but every time they came back and said that that's what is happening. So then we came up with the idea that what is happening is, we were lucky in this case, right? So what we saw is that when you have a pattern, right? Now in this pattern, the molecule, the reactant molecule, what is the reactant molecule seeing? The reactant molecule is not seeing this vanadium, tungsten, whatever, or TBA. The reactant molecule is seeing an oxo surface because you have all the oxygens on the surface, right? So the reactant molecule is seeing an oxo surface. Now when this reactant is coming, it is forming a hydrogen bond with this oxo surface. That's all it is doing. So it's anchoring, right? And then when you are shining laser, then what is happening is there is a hole, an oxygen vacancy that is created on the surface. In the earlier class, you have seen sulfur vacancy for CO2 reduction, right? So here we are seeing, so what Khokon and Rakesh, they saw is that there is an oxygen vacancy on the surface. And because you have oxygen vacancy, what does it mean for the molecule? For the molecule, it means nothing, but it means some electron densities. And then it was possible for the molecule to just replace this nitro with a more reducing, amine, not nitro, amine, with a more oxidizing oxo unit, and then creation of the oxo surface with the concomitant oxidation of this unit. So you have these two parallel things that are going on and that are oxidizing as well as recreation of the surface, because surface cannot be with hole, right? Because hole means there's something vacant. And that's how this whole oxo surface on the SOMS was regenerated, and this cycle continued. So then they determined the oxo vacancy with the lattice oxygen and the oxygen vacancy with XPS, and we were happy to see whatever we were proposing falls into the place. So you see, there are 3 types of reactions which I have shown you so far. So the first one is with benzaldehyde going to benzoic acid. That is very, very simple reaction, goes on with relative ease, right? The first one, that was the one which Preeti did. The second one, which I showed you with Shontu, that was what we did not expect. That was the patterning together with the formation of a plastic conductor, right? We started with pyrrole, and then we were able to form polypyrrole, and then the dopant, the reducing agent actually became the dopant, and this formed this MO2, and then this was the combination of MO2 together with the polypyrrole and polyaniline and forming a conducting surface, and we showed you very high conductance. Now the third one is even more interesting, because here we were able to create oxygen vacancy, right? And with this oxygen vacancy creation, we were able to do a rather difficult reaction of aniline getting converted into nitro, right? So these were the things and we did the Raman spectroscopy before and after and all, and IR spectroscopy, and we were able to show that it's recovered. Now you see, these are some nice pictures to show you, and on the characterization. So this is how the trail looks like. It's a clean trail. And another thing is also important to keep in mind: our trails or patterns we write becomes more and more nice because we are getting more and more experience on how to write patterns, right? So that improves our skills of writing patterns. And yeah, and then we have this type of units, and this was the unit which was present, and then we were able to show that how this reaction is taking place, and we were able to show that we indeed have a composite and which is having this reaction going on. So this has been already published in Materials Advances. So if you are interested, you can have a look at this paper. So what I have tried to show you today with the second lecture is that how you can use microbubble lithography for your reactions, and I have shown you at least 3 different types of reactions. And there is another reaction which we have done, which is a paper under review now, where we have used a MOF based system. This is a work of Kokon, where we have used MOF based systems to do water oxidation. And this is something which we have done, and I hope that next time when I speak with you, I'll be able to tell you more stories. So with this, I stop now, and I'll be very happy to answer your questions. Thank you. Questions or comments or whatever, it's fine. Yeah, I heard something. Oh no. Yes, yes. You should take the mic and introduce yourself and then ask questions.
Hello, I am Dibbujute. I'm a second year BSMS student here at ISER Kolkata. Sir, my question might be a little silly. Actually, I didn't know about the concept of plastic conductors. So, sir, as you mentioned, the conductance is around 600 Siemens per meter, which sounds very little as compared to extremely negligible as compared to the metallic conductance, which is at order of like 10 to the power 6 or 10 to the power 7. So, sir, what are the applications of such materials like plastic conductors?
Yeah, very nice. Thank you. So it's a nice question. So these are the conductors which are conducting, and if you have very small application, very tiny applications, for example in MEMS as actuators and so on, where you need to have tiny changes in the conductivity to so as to activate or actuate your systems, then these type of conductors can become useful. So for example, in small circuits which you would like to prepare, you don't need so massive high conductance, but you need low conductance so as to do this type of actuations. So that's where this can be useful.
So, oh, sir, another question. Actually, I interacted with Khokonda before on DCS day about that micro bubble lithography, but I forgot to ask him some questions. So, sir, does it like the microbubble lithography, does it like improve any Faradic efficiency when we like use microbubble lithography in actual electrolytic setup, like, and we do the reduction process? So does it affect in better, like, does it give better efficiency or something
Okay,
related to?
that's very nice question, very clever question.
No,
And
actually, I did interact with Khokonda, but
yeah,
I didn't interact in details, so that's all.
yeah, that's a very nice question. So what I can tell you, we do not know completely, but what I can tell you from our own thinking, from my own thinking, I'm thinking loud and I'm telling you what is happening. So Faradic efficiency is essentially how much of your turnover, how much of your conversions you are having per coulomb of the charge passed, right? So that's your Faradic efficiency, right? So now if you have a system which is becoming more efficient catalytically, which is being done in the microbubble lithography, right? So that means you have more active surface areas. So I think your Faradaic efficiency will go up. I think, but I might be wrong.
was the actual confusion I had when I interacted with Khokonda. He used this term active surface area, or
Mhm.
that is where I was getting confused. What does actually active surface area
Yeah,
mean?
so they're very good. So there are two types of things which are important to keep in mind in catalysis. So one is the pre-catalyst and the other one is the active catalyst. So what normally you add in your reaction or electrochemical reaction or any reaction is the pre-catalyst. That is not the active catalyst. So for example, in the work that I showed of Nidhi, where we showed this azo type systems, and I showed that this goes into the diradical, that is the active catalyst. So what we mean by that is that you are patterning something which is the pre-catalyst, but when it is undergoing a reaction, it is getting converted into the active catalyst. Now if you ask me what is the nature of the active catalyst, that's very difficult to tell, at least in the ZIF type system, which I anticipate, right? So that's a little bit difficult for me to tell now because we do not know it completely, right? So but that's the difference. And but theoretically speaking, I think understanding it will be like this: your active catalyst, whatever it is, it will be nanoscopic, and in the nanoscopic domain its efficiency will increase, and because it will increase, so the Faraday efficiency should increase. That's my take, but I am open to be proven wrong, and when they do the reaction and get the result, that's we should listen to the data. But very nice, thank you.